In my last video on differential calculus, I went over what a derivative was and what the definition of a derivative is. And using that definition, I showed, but I did not prove, all of these derivative properties on the right side here. And I also showed the derivative of all these base functions over here. Now in this video, I'm going to actually prove all of these. So for that, we're going to need to remember what the definition of the derivative is, because I'm going to be using this a lot to prove everything. So let's just get right started. So let's start by proving all these derivative properties on the right side here. So let's start by proving the constant product rule, which says that when you're taking the derivative of a constant times a function, the constant basically just comes right out and you take a derivative of the function by itself. So that's pretty easy to see. So first of all, I'm taking the derivative of a constant times a function and using the definition of the derivative. Remember that first we have the function at x plus delta x minus the function of x. So I'm going to write that now. So we have c times f at x plus delta x minus c times f at x. And now you can probably see pretty easily that these constants will factor out of this expression, and because the constants don't depend on delta x at all, they can actually just factor right outside of the limit. So the constant factors out, and we'll just be left with this, which is the definition of the derivative for f at x. So that just becomes c times f prime at x. So that's pretty simple. Now let's do the sum and difference rule. So taking the derivative of functions being added together. So over here I'm going to have x plus delta x, f at x plus delta x plus g at x plus delta x minus f at x plus g at x. And now look here. So first of all, I'm just going to bring this negative inside. So that negative will come inside and it'll look like this. And you can see that if I just basically separate these terms, so I'm just going to separate, I'm going to bring the f with the f and the g with the g, and I'm going to separate them just like this. And let me just bring that limit back in. So now a property of a limit is that the limit can go inside of the function into each term individually. So you can bring that limit inside of each of these, and if you bring the limit inside of those, you'll get the definition of the derivative again. So this is just f prime at x plus g prime at x. And if you do the exact same thing with minus instead, so watch, just put a minus here, then this will become minus, this will become a minus, so this will become a minus, this will become a plus. Now if I factor out a minus here, this plus will go back to a minus, and so we would just have these things being subtracted. So both this sum and difference rule and this constant product rule are a property of linear operators. So because the derivative is a linear operator or a linear function, however you want to think of it, something being linear means that constants will factor out, and if they're being added or subtracted together, then you can basically bring this into each of them individually. I'll probably talk about linearity in future videos, but that's not too important right now. So let's do the product rule. So taking the derivative of this, two functions being multiplied together. So I'm going to have f at x plus delta x times g at x plus delta x minus f at x times g at x. Now for this, I'm going to use a trick. Okay, so, and I'm going to do it right between these, so it'll look a little bit nicer. But I'm going to add 0 to this expression, so I'm not going to change anything. The way I'm going to add 0 is I'm going to subtract f at x plus delta x times g at x, and then also add it. And I'm running out of space here, so I'm trying to squeeze this in as best I can. Maybe I'll make this smaller. Okay, so I just added and subtracted the same thing. So these two things actually cancel out, and I'm adding 0. I'm not changing anything. But by adding 0 this way, what I can do is, for these two terms, I can factor out a f at x plus delta x. So you can see f at x plus delta x is in both of those. So I'll go ahead and do that. Factor it out. And I'm also going to separate these fractions too. And then on this side, I'm going to factor out a g at x between these two terms. So this will have a gx out here. And I'll have f at x plus delta x minus f at x over delta x. And now I'm going to do the same thing I did earlier, where I'm going to bring this limit, which is a property of limits, I'm allowed to do this. I'm going to bring this limit into each of these terms separately. So see that this g at x doesn't depend on delta x, so the limit, so this doesn't have to be in the limit at all. So, but this f at x plus delta x has a delta x, so the limit will have to go to here. It'll also have to go to here, and it'll have to go to this term here. So first of all, when the limit goes to this is just f at x. This will become f at x plus 0. So this is just f at x. And then when the limit goes to this term, that's the definition of the derivative again. So that's g prime at x. Again, this g at x doesn't depend on delta x, so nothing happens to it. And when the derivative goes to here, that's the definition of the derivative for f. So that becomes g at x times f prime at x. And if I just rearrange it so it's the same way that I wrote it earlier, then we get the product rule. There it is. So there's also a quotient rule, but the thing is, for the quotient rule, it's much easier to prove it if we know how to do some other things first. So I'm going to prove that last, because I can prove it in a much easier way if we prove some other things first. So I'm going to skip quotient rule for now, and I'm just going to write down to chain rule. So the chain rule is what happens when I have the derivative of f at g of x, so a function of a function. And in my last calculus video, I proved it in kind of like a really physicsy way, which is just basically proving it with notation only, which I'm sure mathematicians wouldn't like, but it works because the whole point, you know, a lot of the ways physicists like to use math is to take advantage of notation. So in this notation, I have these differential operators like df and dx, and they're being divided by each other. df is divided by dx, that gives us the derivative. So thinking of it in this way, I proved I proved the chain rule by just saying, look, if I just write df at x as df by dg times dg by dx, this is the same thing because these dg's effectively cancel and you still have df by dx. So you can basically take the derivative of f with respect to g and then multiply that by the derivative of g with respect to x. But again, this is not very mathematically rigorous, so I'm going to prove it using limits. But you'll see soon that it really is just a matter of notation. If you understand what the notation means, then it is the same thing, really. So I'm going to write g at x plus delta x minus f at g at x over delta x. And I'm going to do the same thing I did in the last video, the same thing I just explained, where I'm going to multiply the top and bottom by dg, which is g at x plus delta x minus g at x. Okay. Multiply top and bottom by it, so I'm multiplying by 1, I'm not changing anything. So first of all, something we need to realize is that I can make a substitution here. I could say, let me do this in a different color. I could say, let g at x plus delta x equal g at x plus delta g. So I can write g at x plus delta x in terms of g at x plus some delta g. So that's the same as me saying, like here's x and then here's x plus delta x. And then here's g at x. This I could write as g at x plus delta x, but I can also just write it as g at x plus delta g, where this is delta g, right? This distance is delta g. And the thing is, when delta x goes to 0, so when delta x goes to 0, that dotted line is getting closer to that dotted line. Then the same thing over here, delta g is also getting closer to 0. So I can make this substitution, and I can also say that when delta x goes to 0, then so does delta g. So yeah, so making that substitution, this is what it would look like, and you'll see why it's useful. First of all, with that substitution, this g at x plus delta x minus g at x is delta g, right? So instead of writing this term as f at g at x plus delta x, I'm going to write it as f at g at x plus delta x, right? Or sorry, delta g. I'm using this substitution here. Okay, minus f at g at x divided by, and again, I'm going to bring this onto this side, and I'm going to bring this delta x over here. So I'm going to switch these. Okay, and this is the definition of the derivative of f with respect to g. Oh wait, sorry. I have to, yeah, so let me make the substitution here too. So I need to go like this, and then over here I'm going to do delta x approaches 0. So I'm bringing the limit inside. With this expression, I'm going to do it with respect to delta g, which is why I made that substitution. And with this, I'm going to still do delta x. So over here, this is the definition of the derivative again. Just instead of delta x, we have delta g. So this is the derivative of f with respect to g. And this is the definition of the derivative of g with respect to x. So that's the proof of the chain rule with proper definition of the derivative. Okay, so now I'm still not going to prove quotient rule. So I proved everything, all these derivative properties except for quotient rule. Quotient rule I'll prove after, because first I want to prove the derivative of these basic functions. So let's start with the derivative of a constant, which hopefully you can just see right away is going to be 0, just because we have c minus c over delta x, which is c minus c is 0. So this is 0 over delta x, which is 0. So this just becomes 0. So that just equals 0. Simple. Okay, now we have the power function, x to the power of any number. The best way I found to prove this is to basically use logarithms. So what I'm going to do is I'm going to do ln of x to the n. And if you remember how logarithms work, properties of logarithms, the exponent can come down and be multiplied by it, and that'll be the same thing. So now I'm going to take the derivative of both sides. So I'm going to take the derivative of ln of x to the n and the derivative of n times ln x. Okay, so over here we have a chain rule situation where we have a function, ln of g, of a function, g, which is equals to x to the n. So that's a little chain rule thing, so I'm not gonna, I'm just gonna do it, and hopefully you can follow along, but I'm using the chain rule. So this is gonna be 1 over x to the n times the derivative of x to the n, whatever that is. And I know I haven't proved the derivative of ln yet. I will do that, so don't worry, we will prove that. But for now, just take it as it is. If you want me to show it again, derivative of ln x is 1 over x. There it is. So I do 1 over x to the n, and then multiply that by the derivative of x to the n, because that's the chain rule. Okay, and then on this side, n is a constant, so that'll just come out, and then I'll just have the derivative of ln of x, which is 1 over x. So remember, this is the derivative we want to find out. So if I just multiply both sides by x to n, I can basically move that x to the n to the other side, and I'll have n times x to the n divided by x. And that, of course, equals n to the x n minus 1. So there's the power rule right there. Okay, next, what's next? All right, the exponential function. So now we're on the road to proving that whole logarithm thing. So I want to find the derivative of some number to the power of x. So I'm going to have a to the x plus delta x minus a to the x over delta x. So that a to the x plus delta x equals a(x) times a to the delta x, if you just remember how exponents work. And of course I can factor out an a to the x, and this a to the x doesn't depend on delta x, so it'll also factor right outside of the limit. So I'll just get this, a to the delta x minus 1 over delta x. So now we have to figure out what this limit is. If I just plugged in delta x equals 0, a to the 0 would be 1, 1 minus 1, this would be 0, and then the bottom would also be 0, so it would be 0 over 0, it would be indeterminate. So we have to figure out some way to compute this limit. The way to do that is to make a substitution. So the substitution we're going to make is we're going to let that numerator, x to the delta x minus 1, equal y. Doesn't matter what we call it, I'm going to call it y. So that means that y plus 1 equals a to the delta x. And if I take the logarithm of both sides, the natural logarithm of both sides, then again, I can bring that delta x down. This will be ln a, which means that delta x equals ln of y plus 1 divided by ln a. So so wherever a to the delta x minus 1 is, I'm going to put a y, and wherever delta x is, I'm going to put this here. So let me just write that in. So we have a to the x times the limit as delta x approaches 0, and at the top we have y, underneath we have ln of y plus 1 divided by ln of a. So first of all, I'm going to bring this y to the bottom and bring this ln a to the top. So this becomes ln a goes on top. This becomes 1 over y on the bottom. And because this ln a doesn't depend on delta x, I can bring this limit into the denominator by itself. Oh, I forgot to do one thing. When I made the substitution, I have to show that when delta x goes to 0, y also goes to 0. So, okay, so if I put in 0 for delta x, this becomes 1 minus 1, which becomes 0. So, as delta x approaches 0, then y also approaches 0. So now when I make the substitution and put everything in terms of y, I have to also substitute that delta x in the limit. Forgot to do that, but here it is. So as delta x approaches 0, y is also approaching a 0. So I made a substitution. Everything's now in terms of y. And again, like I said, because this ln a doesn't depend on y, then I can bring this limit as y approaches 0 into the denominator alone. So this will be ln a on top divided by the limit as y approaches 0. And again, I'm going to use that property of exponents and limits to bring this factor onto the exponent there. So this becomes ln of y plus 1 to the power of 1 over y. And let me write this actually like 1 plus y. And if you don't know, this, or sorry, actually, let me bring the limit in one more time. Because again, I can bring this limit, property of limits is I can bring it into the function. So I can bring this limit into the logarithm. So I'll have the natural logarithm of this expression here. And there it is. This is the definition of E, Euler's number. You know, I could do a separate video on that, of what E is and why that's the definition. Another definition you might have seen, which is equivalent, is the limit as x approaches infinity of 1 plus 1 over x to the power of x. This is actually the same thing. If you just make the substitution, 1 over y equals x. But yeah, so this is actually the definition of E. So I can just replace this with a to the x. We have ln a on top, and on the bottom we have ln of E. And the natural logarithm of E is just 1. So this becomes 1. And finally we just have x, a to the x times the natural logarithm of a. And from that, it's pretty easy to prove what happens when a is E, the Euler's number, because again, ln of E is 1. Sorry, I should be writing derivative here. So the derivative of e to the x is just e to the x, because this is just 1. Okay, now let's go ahead and prove the inverse of the exponential function, the logarithmic function. To do that, I'm going to use what we already proved, which is the derivative of the exponential function. So here's how I'm going to do that. First of all, if we just understand how logarithms work, if log a to the x equals y, then that means that a to the y equals x. Okay, so I want to find the derivative of log a to the x, which means I want to find the derivative of y. So what I'm going to do is, let me find the derivative of both sides of this expression. So dx by dx is 1. You can see that from the power rule, or you can see the fact that dx divided by dx is 1. So that's another notation thing. Or you can use power rule. Bring the 1 down and subtract 1 off the exponent. You would have 1 times x to the 0, which again is 1. So this side becomes 1. And then this side, we have a to the y times ln a. And this is chain rule because y is a function of x. So I took the derivative with respect to y. Now I have to multiply that by the derivative of y with respect to x. And remember, y equals log a to the x. So the derivative of y is exactly what we're trying to find. So I divide both sides by ay ln a. And look at this. What did a of y equal? A of y equaled x. So the derivative of y, which is log a base a of x, equals 1 over x times ln a. And again, if you plug in a equals e, you will then get the derivative of the natural logarithm, which is 1 over x, because ln of e equals 1. All right, now, maybe before I go to the trig functions, let me just use what we know already to prove the quotient rule. Because we know everything we need to know due to the quotient rule. So for quotient rule, so f divided by g, I'm going to write this as a product of f times 1 over g. So now I'm going to use product rule. So I take the derivative of the first times the second plus the first times the derivative of the second. So for the derivative of 1 over g, let me just do that on the side here. So first of all, 1 over g is the same as g to the negative 1. So we have a power function. And again, we have to use chain rule because g is a function. Or sorry, g to the negative 1 is a function of g, which is a function of x. So this is a function of a function. So I'm going to bring the negative down. I'm going to subtract 1 off the exponent. So it's g to the negative 2 times the derivative of g with respect to x. So that becomes negative g prime over g squared. So I'm going to write that there. So this becomes a negative g prime divided by g squared. And now if I just multiply the top and bottom of this term by g, I'll get f prime g over g squared minus fg prime over g squared. And now I can just bring these fractions together and I get the quotient rule. So for the quotient rule, I wanted to prove the power rule. And yeah, I guess just the power rule, just so we could use it. Now on to the trig functions. So let's do sine. Okay, so again, let's write out our definition. So sine of x plus delta x minus sine x divided by delta x. Now you have to remember the sum identity for sine. That is sine of alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. So that's a little trig identity that we need to know to do this. So this is sine x cos delta x plus cos x sine delta x minus sine of x. Okay, so let's collect some like terms here. So if we look at this term and this term, I can actually factor out a sine x. So I'm going to factor out sine x out of those two terms. And I'm going to separate them also. And now I can bring that limit inside. So I'll bring the limit into each term that the limit shows up, or that delta x shows up. So it shows up there, and then I'm going to have plus cos x. Then I'm going to have the limit again there. Okay, so now just like before when we were doing exponential stuff, we need to find a way to prove this limit. And proving this limit will also allow us to prove this limit pretty easily after that. So this is going to be a little more complex, so let's break this down. So to compute, so we want to compute this limit. I'm going to do this separately here. We want to compute the limit of sine theta over theta as theta approaches 0. For this, we're going to have to use a special tool called squeeze theorem. What squeeze theorem says is if I have some function f of x, which is always between two other functions, which I'll call g of x and h of x, then if the limit as x approaches some number a, if that limit of g of x equals the same limit of h of x, which equals some number L, then the limit as x approaches a of f at x has to equal L. So the reason is we have some function, we have what I call, which is less than. Okay, so G and H. And F is always between them. Okay, so here's F. So F is always between G and H. Now, if H of X and F of X approach the same limit, L, so they're both approaching L when X approaches A, so there's A, here's L, then that means that when F approaches A, it also has to approach L, because F is always between those two functions. So it's called the squeeze theorem because H is always above F and G is always below F, so they both kind of squeeze F to one limit. So if you can't figure out the limit of f at x, you can find two functions that are less than or greater than f, and if you compute their limits, then if those limits are the same, then you know that what f's limit is. So that's the strategy we're going to use. So to do this for sine, we're going to do this geometrically. So what I'm going to draw is a unit circle. So hopefully you are familiar with trigonometry, because this proof is going to be full of it. Okay, so I'm going to draw a unit circle here. So here's the unit circle. It has radius 1, and this angle is theta. And this height here, this height is sine theta. Now, first, I want to compute the area that I'm outlining here in blue. So this triangle that I've drawn in blue has a base of 1, the base is the radius 1, and a height of sine theta. So this blue area equals the magnitude of sine theta. So it's base times height divided by 2 for area of a triangle. So the base is 1 times the height, which is sine theta, and I have to put magnitude signs around it because I'm dealing with actual physical lengths, right? This is a geometrical proof, and sine theta can be negative sometimes. So I want the magnitude of sine theta. I don't want a negative number. These are actual physical lengths I'm dealing with. So it's the base times the height divided by 2. So that's the area of the blue, of the blue triangle there. Now I want the area of this shape right here. So the shape that I'm outlining is like, it's like if I took a slice of pie out of this whole circle, right? So this length, this arc length of this slice of pie, if you remember what radians are, if theta is measured in radians, then this is the radius times theta. Because when theta is measured in radians, the angle in radians is saying how many radii this arc length traverses. So if the radius, if theta is 1, then that means that this arc length is 1 radii long, or 1 radius long. So that's what the radian means. So we use radians so we can do these easy arc length computations. So the area of this red pie slice here, we can get by taking the area of the circle, which is pi r squared, and multiplying it by the proportion that that pie slice is out of the circle. So to get that, we can do the arc length divided by the total circumference. And its arc length is r theta. So this is like the fraction of the circle that that slice of pie takes up. So if I multiply that by the area, then I'll get the area of just that pie slice. So first of all, the radius is 1, so all these r's cancel out, they're all 1. And then this pi will cancel with this pi, and we'll be left with theta over 2. And again, we have to use absolute theta, because theta can be negative sometimes. But we need actual physical lengths here, we need magnitudes. So the area of the red slice of pie there is theta, or the magnitude of theta over 2. And now I'm going to take the area of one more triangle. So this is going to be this triangle here. So this green triangle has the same base as the blue triangle, 1. And its height here, let's figure out what this height is. So I'm going to call this L for now. Notice that tan theta is the opposite side of the right triangle, L, divided by the adjacent side, 1. So that means that L equals tan theta. So now if I want to find the area of the green triangle, I do base, which is 1, times the height, which is tan theta, divided by 2. So now notice that this blue triangle here, the area, is always smaller than the area of the entire slice of pie there. And further, this green triangle has an even bigger area than both of those. So the blue area is less than or equal to the red area, which is less than or equal to the green area. So that means that sine theta over 2 is less than or equal to theta over 2, which is less than or equal to tan theta over 2. Now I'm going to multiply everything by 2 to get rid of those. And I'm going to rewrite that tan theta in terms of sine theta and cos theta. Now I'm going to divide everything by sine theta. And I'm trying to make this as simple as possible, but when you're dealing with these less than or equal than signs, if you do something to the expression that is a decreasing function, you have to switch around the signs. So I haven't done anything to this expression that is a decreasing function yet, but I'm about to. I'm about to take the reciprocal of all of these. Now when I take the reciprocal, I'm doing 1 over x, and 1 over x is a decreasing function. And I'm not trying to get too much into this right now, but I feel like a lot of people aren't familiar with how to use the less than or equal to signs. But if I do something that's a decreasing function to it, I have to flip around all those signs. So the reciprocal of 1 is 1. This will change to a greater than or equal to. This reciprocal is sine theta over theta. Again, that sign flips. And this is cos theta. So now I have this. And now I can actually get rid of these absolute signs because they actually do nothing for the situation I'm in. Remember that theta equals 0 is right on this horizontal line. Right on that horizontal line, theta equals 0. So I can either have theta going close to 0 from this first quadrant, or I can have negative theta going to 0 from that fourth quadrant. Either way, in the first quadrant, sine theta is positive. The y value is positive. So that would be positive. So sine theta would be positive, theta would be positive. It would be positive anyways. For this quadrant, sine theta, or the y value, is below 0. So in this quadrant, sine theta is negative, but theta is also negative. So this is negative divided by negative. So that would also be positive. And also, in both these quadrants, the x value is positive, or cos theta is positive. So these absolute signs actually can go away. They don't do anything. So I can just write this. And now I can finally use my squeeze theorem. The limit as theta approaches 0 of 1 equals 1, of course. The limit as theta approaches 0 of cos theta equals 1. So these both equal 1. And sine theta over theta is always between these two, which means that by the squeeze theorem, the limit as theta approaches 0 of sine theta over theta has to equal 1. And for this limit, the limit of cos theta minus 1 divided by cos theta, I can also get, so first of all, let me multiply top and bottom by the conjugate, cos theta plus 1 times cos theta plus 1. So this will become, if I multiply these out, this will be cos squared theta minus 1 on the top. On the bottom, I'll have theta times cos theta plus 1. And this here equals negative sine squared theta. If you just remember that, sine squared plus cos squared equals 1. Then you can see that the top there is in fact negative sine squared theta, which instead of writing negative sine squared theta, I'm going to write sine theta sine theta. And for one of the sines, for one of the sines, I'm going to keep it with this theta, and for the other one, I'm going to keep it with this cos theta plus 1 on the bottom. So I'm going to split these up, and what I'll do is I'll just bring this negative into this bracket here. So this will be the limit, which we already know what it is. This is 1, this limit, right? We already solved this up here. Okay, times, again, I'm bringing these limits inside, sine theta over 1, or actually, I don't know why I said I was going to bring the negative in. That won't really do anything. So I'm just going to keep the negative there. So this limit becomes 1. This, if I plug in theta equals 0, so this limit, if I plug in theta equals 0, sine of 0 is 0, so the top is 0. The bottom, cos of 0 is 1, so 1 plus 1 is 2. So this is 0 over 2, which is just 0. So that becomes 0. So the limit as theta approaches 0 of cos theta minus 1 over theta equals 0. So these are the two limits we need to finally prove our derivative rule for sine. So let's go back up here. Let's look at sine. I'm going to erase this whole squeeze theorem thing. And let's plug in what we know. So this limit is 0. So that's times 0. Plus cos x. And we know that this limit is 1. So that just becomes cos x. The derivative of sine x is cos x. Okay, and now if we do the same thing for cos x, it's going to be the exact same thing, honestly. So let me just do it really quickly. So I'm going to have cos x plus delta x, which, if I use the identity to split up that sum, it'll look like this. Okay, and then it's minus cos x over delta x. So I just use this identity here, cos a plus b equals cos a cos b minus sine a sine b. And now I'm going to factor out a cos x out of these two terms. So I'm going to factor the cos x out of there. I'm going to have cos delta x minus 1 over delta x, and then minus sine x sine delta x over delta x. Okay, now if I bring these limits in, I know the limit, when I bring it into that, that'll become 0. That'll go away. And when I bring the limit into this, that'll become 1. So this will become negative sine x. Okay, so now for tan x, it's not too bad because tan x can be written as sine over cos. So this is the derivative of sine x over cos x, which, just like I did for the quotient rule, I will write it as sine x times cos x to the negative 1. So now I just use product rule. So I do derivative of sine, which is cos x, times cos x to the negative 1. And these, of course, just cancel out. So that'll become 1. Plus sine x times the derivative of cos to the negative 1x. So I do chain rule. This is negative cos x to the negative 2 times the derivative of cos x, which is negative sine x. Okay, so this is 1. These negatives will cancel, so this will become plus sine squared x over cos squared x, which is 1 plus tan squared x. And this is the same as secant squared x, if you remember that identity. So 1 plus tan squared x equaling secant squared x is another very important trig identity that everyone should know. But yeah, so that's the derivative of tan. And now finally, we just have to do the derivative of all the inverses. So for that, I'm going to say let y equal sine of x, which means sine negative 1y. Or actually, no. Let me do it the opposite way. I want to find the derivative of sine to the negative 1x. So I'm going to let y equal sine negative 1x, which means sine of y equals x. So now I'm going to take the derivative of both sides. So the right side becomes 1. The left side, take the derivative of a sine with respect to y, and then y with respect to x. That's the chain rule. Equals 1. So dy by dx, which is what we want to know, since y is sine negative 1 of x, equals 1 divided by cos of y. And cos of y is the same as the square root of 1 minus sine squared of y. That's the Pythagorean identity. And remember that sine of y equals x. So this is 1 over the square root of 1 minus x squared. Okay, pretty simple. Again, I want to do cos negative 1 of x. So I'm going to let y equal cos negative 1x, which means that cos y equals x. Now if I take the derivative of both sides, this becomes negative sine y dy by dx equals 1, which means d by dx of y, which is cos negative 1 of x, equals negative 1 over sine y. And sine y is the same as 1 minus cos squared y. And cos y is x, so this is negative 1 over square root of 1 minus x squared. Okay, and now last but not least, we have tan negative 1. And I'll do the exact same way. So y equals tan negative 1 of x, which means tan of y equals x. I take the derivative of both sides. Derivative of tan y is secant squared of y times dy by dx, which equals 1, which means d by dx of y, which is tan negative 1 of x, equals 1 over secant squared of y. And remember that identity, that 1 plus tan squared equals secant squared. So this is the same as 1 over 1 plus tan squared y. And tan y is x. So this is equal to 1 over 1 plus x squared. And there it is. That's all of the derivative properties proved, and the derivative of all these main basic functions that you'll need to know also proved. Thanks for watching.